and thanks to the organizers for giving me the opportunity to present my research. So I'm presenting this based on my master thesis that I did, which I did with my supervisor, Professor Klaus Kiefer. Because quantum gravitational effects are going to be significant at very high energies, one of the best places to look for the contributions is the early universe. So therefore, we hope to see some effects in the power spectrum of anisotropies of CMB. So, as you know, there are different approaches to quantize gravity. So the approach that I'm going to use is canonical quantum gravity. In addition, as you noticed from the title, I'm going to discuss closed model of the universe. I'll give some motivations. Why is it important and interesting to look for closed model of the universe? And then canonical quantum gravity starts with Hamiltonian formulation. Therefore, because we are considering the power spectrum, which is assumed that it has been originated, the anisotropies of CMB are assumed to be originated from inflationary fluctuations. Therefore, we start with Hamiltonian formulation of the inflationary Friedman universe. Then I'll introduce a gauge invariant variable, curvature perturbations, and explain why is it important to discuss them. The quantization of after this stage, after Hamiltonian formulation, leads us to the Wheeler-DeWitt equation. And instead of trying to solve this directly, we will apply semiclassical approximation and study it using this approximation. And after this approximation, we can derive the power spectrum for uncorrected one and quantum gravitationally corrected cases. And I'll finish with conclusion and outlook. Okay, as you know, the lambda CDM model is very favored from the Planck data, but there is current discussion why it is not obvious that the universe should be flat. And there are these recent papers published, and also there are more other papers that I don't mention here. You can see the other references in the paper. So there is current discussion about correct interpretation of data, and the indications were found that speak in favor of especially closed universe. Particularly, the authors of this paper claim that from Planck data, the positive curvature explains the anomalous lensing amplitude, and it also removes tension within the Planck data set concerning the values of cosmological parameters derived at different angular scales. Also, it's expected that the closed model might explain the observed low amplitude of quadrupole and octupole modes. As you can see, indeed, from this picture, this curve is for the flat model, so you can see that there is a lack of amplitude here. So we are hoping that a closed model will explain this part. Okay, so since I'm going to apply canonical quantum gravity, let me give very briefly how we have to construct it. So we start with Hamiltonian formulation of GR. For it, we have to foliate the space-time into space-like hypersurfaces. Hij is the tree metric induced on this hypersurface. Ni is the shift vector, and n is the Leibniz function. So n describes the temporal evolution, and Ni describes the spatial evolution. After substituting this into Einstein-Hilbert action, using the fact that and taking the variation with respect to Leibniz and shift, we will get these two constraints. The first constraint is known as Hamiltonian constraint, and the second one is known as diffeomorphism constraint. So the first one is obtained after taking the variation with respect to the Leibniz, and the other one with respect to the shift. So yeah. Oh, sorry. Yeah. Now that we have this Hamiltonian formulation, we have to quantize the system. So we have to take a canonical coordinate and the corresponding momentum and take them as operators. And according to the procedure of quantizing the constraint systems is to take the constraint as an operator, act on the wave functional, and set this equal to 0. So from the first one, we will obtain Wheeler-DeWitt equation, which follows from this Hamiltonian constraint. And the second one is known as quantum diffeomorphism constraint. Also note that in Wheeler-DeWitt equation, there is no notion of classical time. So because that is because of the reparameterization invariance of the theory. But then I'll show that after the semi-classical approximation, we can introduce the notion of time. Yeah, and also let me mention that, as I said, we have to choose canonical coordinate and momentum. So the coordinate is the induced metric on the hypersurface. Okay, now we have to apply this on our specific case. So we are considering the FLRW line element. And so because of the symmetry, the shift is not entering here. We have only the Leibniz function here. Yeah, so now using this line element into the Einstein-Hilbert action plus the matter. And for the matter, as you know, the inflaton is a scalar field. So particularly, we are considering quadratic potential here. So we will get the following background Hamiltonian, following the steps that I presented in previous slide. So yeah, so P alpha is the momentum related to the scale factor, and we introduce this alpha parameter as follows. Yeah, so we have the background, the geometric part plus the meta part here. Because our goal is to calculate the power spectrum of the fluctuation, we also have to introduce perturbations. So including perturbations of the metric and also the scalar field. Halliwell and Hawking showed that this Hamiltonian, the total Hamiltonian, can be written as sum of the background part plus perturbation parts. And also one obtains also the first order Hamiltonian constraints. The problem with this is this form is not gauge invariant. To be able to work with physical quantities, we have to introduce gauge invariant variable. This has been done by David Langlois in 1994, and he obtained the following form for the perturbation Hamiltonian. So Qn is the gauge invariant variable, and Pn is its conjugate momentum, and Un and Wn are some functions of the alpha and phi. Because this form is not very convenient to work with, I performed a canonical transformation as follows, and we can bring the Hamiltonian in very compact form. And we have this Vn tilde, a new gauge invariant variable, which we call generalized Mukhanov-Sasaki variable. And to make sure that we are in a right track, if we take the large wavelength limit, we see that we can recover the result for the flat case. And this Vn tilde becomes the Vn, which is Mukhanov-Sasaki variable. Okay. Now we have this gauge invariant variable we introduced with this Vn tilde, but to be able to relate our power spectrum at the end of inflation to the angular power spectrum of CMB, we have to introduce another gauge invariant variable, is zeta BST, which is given by this form where phi is the Bardeen potential. In a flat case, one can use this zeta instead of zeta BST, but in a closed case, this is not conserved, which is why we have to use this variable instead of zeta, unlike the flat case. So as I said, we are interested to obtain the power spectrum of curvature perturbations. Therefore, we relate these curvature perturbations to our gauge invariant variable, so that as soon as we obtain the power spectrum of Vn tilde, we can directly, using this relation, obtain the power spectrum of zeta BST. Okay. Now we are using a slow roll approximation, which is well suited to the observations. So the condition is that the kinetic term must be vanishing compared to the potential term. So using also this approximation, as I said, to obtain the Wheeler-DeWitt equation, we have to take the total Hamiltonian as an operator, act on the wave functional, and set it equal to 0. As you can see, we have here separately the background part entering and also the perturbation part entering. And omega m square is given like this. So you can see the explicit and additional contribution because of the curvature. And again, if you take the large wavelength limit, we can recover the result for the closed case, for the flat case. Also, I should mention that to obtain this, I have also used the following ansatz. So assuming that different modes do not interact with each other, we can obtain this Wheeler-DeWitt equation for each mode. Now, to study the Wheeler-DeWitt equation, we apply a semi-classical approximation. We start with making this WKB-like ansatz as follows. Then the Born-Oppenheimer approximation is implemented by expanding this function of alpha, phi tilde, and Vn tilde in terms of powers of Planck mass, like this. So the idea that we can use this Born-Oppenheimer approximation is based on the fact that because we have this background dynamic, this geometry, we can treat it as heavy part, and we can treat the perturbations as the light part. Okay, so now we have to substitute this into the Wheeler-DeWitt equation, gather all the corresponding powers of Planck mass, and then at each order we will obtain the following equations. So first, at the order of mp to the 4, we obtained this condition that this S0 is independent of Vn tilde, which basically means that the background spacetime is independent of the perturbations as expected. At the next order, we obtain Hamilton-Jacobi equation for the background, which is equivalent to the Friedmann equation. So classical GR. At the next order, at mp to the 0, we obtain this Schrodinger equation. So actually, we So we actually obtain an equation for S1. After doing some transformations, we can end up with this Schrodinger equation as expected. So now we have a classical background and quantum perturbations propagating on that classical background. Basically, we have QFT inverse spacetime here. So as I said, we don't have fundamentally notion of time in Wheeler-DeWitt equation. So here we can introduce time again by this relation. At the next order, we can obtain also quantum gravitational corrections to the Schrodinger equation. So this is the corrected Schrodinger equation. Also, I want to draw your attention into this term. So there is the unitarity violating term here. One should not worry about this because it has been shown by Leonardo Chatenier and his collaborator that this term can be absorbed within the definition of inner product. But for this work, we just dropped this. But then in the future, we are planning to treat this properly by redefining the inner product. Now, so basically, we have to solve these two equations, the uncorrected Schrodinger equation and corrected Schrodinger equation. To do that, we start with making the Gaussian ansatz for the Schrodinger equation, and we end up with this Riccati equation. And doing the similar thing and introducing a Gaussian ansatz also for the corrected wave functional, we obtain this equation. So at this point, we have to solve these two and obtain the power spectrum. So for the uncorrected case, by starting with a two-point correlation function, one can show that the power spectrum of Vn tilde is given by this. So we see that the real part of omega n0 enters here. So by solving the previous equation that I showed and taking the real part of it and substituting here, we obtain the following result for the power spectrum in closed case. And unlike the flat case, you see that also this K enters here explicitly. Yeah. As I said, is vital to have this power spectrum of curvature perturbations as well. And using the relation that we obtained for theta BST and Vn tilde, we can obtain this final result of the power spectrum of curvature perturbations. And to see what kind of effect we get from this plot, where this dashed line is representing the flat case, and this thick line represents the closed case, we see explicitly there is a significant suppression of power for large scales. And also there is this cut here, that is because of the finiteness of the universe. So I should also point out that from this power spectrum, one can see that because of the explicit scale dependence, the power law approximation that is widely used to study the Planck data is not applicable, at least for the large scales. Therefore, in the codes, one have to substitute this power spectrum instead and analyze the data based on that. This is what I'm planning to do with Eleonora Di Valentino soon. Yeah. So now let's see what kind of corrections we get for the power spectrum. The power spectrum for the quantum-gravitationally corrected case will be given by this. And after substituting and solving the equations and substituting the values of omega n0 and omega n1, we can write it like this. So we have uncorrected power spectrum and times 1 plus entering this small contribution from quantum gravity. Which is given by this. Again, to check if our results are correct and we are on the right track, we again can take the large wavelength limit, and we see that we recover the results obtained by Kiefer and his student for the flat case. And they already have estimated that this contribution is actually very, very small. And because this contribution is mainly in the large scales, where we have the problem with cosmic variance, and we have huge error bars because of this, unfortunately, we do not expect to be able to observationally claim this contribution. Yeah, to sum up, so first we derived the Wheeler-DeWitt equation for the inflationary universe, then we applied semi-classical Born-Oppenheimer type of approximation. At the corresponding orders of approximation, we recovered both uncorrected and quantum-gravitationally corrected power spectra. The angular power spectrum can only be calculated by sophisticated numerical methods. And by employing a closed model, one might be able to explain the observed lack of power for large scales. And also, due to the smallness of the quantum gravitational corrections to the power spectrum, we do not expect to confirm them by observations. So this was it. Thank you very much.
Any questions to the speaker? Okay, there is one there by Jorma.
So these Friedman models with a positive spatial curvature, the spatial topology is naturally closed.
Yeah.
Whereas for the zero or negative curvature, you have some choice. I mean, the spatial topology comes naturally as non-closed, but you have the choice to make it compact if you like.
Yeah.
So in your results, is the key feature in the curvature, or is it in the choice of the topology?
No, it's just coming from the curvature itself without considering. So we have the most basic topology here. It's just spherical universe, and that's it. So spherical space-time, yeah. Of course, one can also consider different types of topologies, as you mentioned, but yeah, I'm not aware of what kind of results they get, but this is just pure from this curvature coming. Yeah.
Thank you.
More questions?
Hi, thank you for the talk. I have a question. So now your result is that the corrections to the power spectrum are of the order of 10 to the minus 10.
Yeah.
But you said that you won't be able to detect this, and yeah, I understand that, but you can also compute corrections to the running of the spectral index. As you said, this kind of k-dependent power spectrum will induce a correction in the power law ansatz that people usually do.
But the problem is for the closed case, this ansatz is not applicable because this ansatz is based on the assumption that this there is no explicit scale dependence. So because we have explicit scale dependence, it is not applicable. Maybe for the flat case, one can like go further and see whether, as you mentioned, into running and etc., you can get bigger results, but I don't really expect it to happen. And also, maybe to go back. Yeah, here, as you can see, the main contributions are in this region where we have these huge error bars because of the cosmic variance. So that's why you don't really expect, even for the closed, the contribution of the power spectrum because of the finiteness of the universe. Even that, if you just plot and show, okay, we have this suppression because of this huge error bar, still you cannot claim that, okay, this is 100% the case. So that's why you don't really, you can't really claim anything in this region.
Okay, thank you.
Sure.
Okay. Last question.
Thank you. So, and my question about your approximation method. So, and can you have R or any illustration in which the approximation is valid and you can get non-trivial correction which can be measurable somehow? Can you imagine that?
If I understood you correctly, so this approximation is valid because you have these tiny perturbations, right? It's always that you can treat them as kind of light part and you have the heavy part. That's why this is like what you can do. And it's not that some kind of weird approximation that you apply and you don't, that because of that approximation, you don't see this contribution. So yeah, I think it's perfectly valid in this case, and I don't see any other kind of option to really discuss. And also it is not that kind of easy to directly solve the Wheeler-DeWitt equation and see what happens. So this is something that we have to rely on.
Okay.
Yeah.
Other than context of the universe, cosmological context, other than.
Well, you have to see like, I mean, there are different approaches to Wheeler-DeWitt equation, how to treat them, etc. But like in our specific case, this is like what you can do and what is valid, in this scenario.
Thank you.